Alright, let's talk about something you can't see, but that shapes your world every single day. I'm talking about electromagnetic waves. These waves are all around us. They carry your favorite radio station, heat up your lunch in the microwave, and let your phone connect to the internet. Now imagine you had a special kind of screen or filter. This screen is very picky. It lets some waves pass right through but blocks others completely. That, in a nutshell, is a frequency selective surface, or FSS. It's a smart surface that acts like a bouncer at a club, deciding which frequencies get in and which have to stay outside. It's a fundamental tool for controlling the invisible. Think of it like a window screen for light waves, but much more sophisticated. A simple window screen stops insects, but lets air and light pass through. An FSS does something similar with electromagnetic energy. It's designed to interact with specific frequencies, the color of the radio wave, so to speak. Depending on its design, it can be a filter that lets a certain band of frequencies pass, which we call a band pass filter. Or it can be a filter that blocks a certain band, which we call a band stop filter. This simple idea of selecting frequencies is incredibly powerful and is the secret behind many technologies you use without even realizing it. So, where does this magic come from? It's not magic, it's physics. An FSS is typically a thin sheet or surface printed with a repeating pattern of metallic shapes. These shapes are like tiny antennas. When an electromagnetic wave hits the surface, these little metallic elements resonate or vibrate in response. The size, shape, and spacing of these patterns are all carefully calculated. They are tuned to react to very specific frequencies. If the wave's frequency matches the resonant frequency of the pattern, the surface will reflect it. If it doesn't match, the wave can pass through as if the surface wasn't even there. This ability to control waves is not just a neat trick, it's essential for our modern connected life. It helps us manage the increasingly crowded airwaves, ensuring that different signals don't interfere with each other. Look around you. Your Wi-Fi router, the satellites orbiting Earth, the stealth technology on military aircraft, they all rely on this principle of frequency selection. An FSS is the unsung hero that directs this invisible traffic, making sure your video call is clear and that a pilot's radar sees what it needs to see. It's a core piece of engineering that makes our high-tech world possible. Let's dive a little deeper into the classic FSS designs. The traditional ones are beautiful in their simplicity. Picture a flat surface like a circuit board with a repeating pattern of simple metallic shapes. These shapes are often basic geometric forms you learned about in school. Squares, circles, crosses, or dipole shapes that look like little dumbbells. These patterns are arranged in a regular, grid-like fashion, covering the entire surface. The key rule for these traditional designs is that the size of each shape is directly related to the wavelength of the frequency it's supposed to block or pass. To interact with a long wavelength, you need a large shape. The way these surfaces work is all about resonance, a concept you see everywhere in the universe. When an incoming wave hits the FSS, the metallic elements start to oscillate. If the wave's frequency is just right for the size and shape of the metal patch, it creates a strong electrical current in the pattern. This strong response causes the surface to act like a solid metal wall for that specific frequency, reflecting it away. For all other frequencies, the elements don't respond as strongly, so the waves can travel through the gaps between them. It's a straightforward and effective method that has served engineers well for decades. You can find these traditional FSSs in many places. One of the most common applications is in radomes, the protective domes that cover radar antennas on airplanes and ships. The radome needs to be transparent to the radar's operating frequency so the signal can get out and back in. However, it might need to block other frequencies to prevent interference or for stealth purposes. So, an FSS is embedded right into the radome structure. Another classic use is in satellite communications, where giant reflector antennas on the ground use FSSs to handle multiple frequency bands at once, separating signals for television, internet, and phone services. However, these traditional designs have their limits. The biggest one is their size. Because the elements have to be about half a wavelength long, filtering low-frequency signals requires very large, bulky surfaces. Imagine trying to build a filter for a radio wave that's several meters long. Your FSS would have to be huge. This makes them impractical for small portable devices. Furthermore, their performance is often fixed. Once a traditional FSS is built, it filters one specific frequency band. It's not very adaptable if you need it to change its properties on the fly, which is a big drawback in our fast-evolving technological landscape. Now let's get to the really exciting part. What if we could break the old rules? What if we could design surfaces that control waves in ways nature never intended? Welcome to the world of metamaterials. A metamaterial is an engineered material with properties not found in nature. It gets its abilities not from what it's made of, but from its structure. By arranging tiny, intricate structures in specific patterns, we can create a material that can bend light backward or become invisible to certain waves. When we apply these mind-bending ideas to FSSs, we get something truly revolutionary: metamaterial-inspired FSSs. The biggest difference lies in the design of the tiny elements on the surface. Instead of simple squares or crosses, metamaterial-inspired FSSs use much more complex, intricate shapes. These are often called sub-wavelength resonators because they are much smaller than the wavelength of the energy they control. Think of shapes like split-ring resonators, which are kind of like an incomplete circle with a tiny gap or spiral patterns. These complex geometries can trap and manipulate electromagnetic energy in very sophisticated ways. They can create strong resonant responses even though they are incredibly small, which is the key to their power. This ability to be small is a game changer. It's a process we call miniaturization. A traditional FSS designed to filter a 1 GHz signal might need elements that are several centimeters wide. A metamaterial FSS doing the same job could use elements that are only a few millimeters wide. This is a massive reduction in size, allowing us to build powerful filters that can fit inside a smartphone, a small drone, or a medical implant. We are no longer constrained by the wavelength of the signal. Instead, we are only limited by our imagination and our ability to manufacture these tiny, complex patterns. Beyond just being smaller, these new designs offer vastly improved performance. They can be designed to be multi-band, meaning one single surface can filter several different frequency bands at the same time. Some can even be made tunable or reconfigurable. By adding active components like diodes to the tiny elements, we can apply a small voltage to change their resonant properties. This means we can change what frequencies the FSS blocks or passes in real time. It's like having a programmable filter, which opens up a whole universe of new possibilities for dynamic and adaptive technologies. So where can we use these advanced metamaterial-inspired FSSs? The applications are as vast as the electromagnetic spectrum itself. One incredible example is in the realm of secure communications and architecture. Imagine a building with windows that look completely transparent to your eyes, letting visible light in. However, these windows are coated with a nearly invisible FSS. This FSS is designed to block Wi-Fi and cellular signals from getting in or out. This creates a secure bubble inside a room, preventing any unauthorized wireless snooping or data leakage. It's called smart glass, and it provides security without turning a room into a windowless bunker. Another amazing application is in next-generation satellite technology. Satellites need to communicate using many different frequency bands for GPS, data transmission, and Earth observation. Using traditional FSSs would require multiple large antennas and filters, adding a lot of weight and complexity. A single lightweight FSS built with metamaterials can handle all these tasks at once. It can separate and direct different signals to the right processors on the satellite. This makes satellites smaller, lighter, and cheaper to launch, which is crucial for building the vast constellations of satellites needed for global high-speed internet, like Starlink. The impact of these tiny, powerful surfaces extends even further. In medicine, they could be used to focus microwave energy more precisely for therapeutic treatments, targeting cancer cells while leaving healthy tissue unharmed. In defense, they are essential for creating advanced stealth technology that can adapt to different radar frequencies, making aircraft virtually invisible. The ability to finely control electromagnetic waves at a miniature scale is not just an incremental improvement, it's a giant leap forward. It allows us to build smarter, smaller, and more capable devices than ever before. As our world becomes more connected and dependent on wireless technology, the electromagnetic spectrum gets more and more crowded. Managing this invisible chaos is one of the great engineering challenges of our time. Metamaterial-inspired FSSs are one of our most powerful tools for bringing order to that chaos. They are the gatekeepers of the future, enabling everything from faster wireless networks to more secure buildings and more efficient space exploration. The universe is full of waves. By learning to build these tiny, intricate surfaces, we are becoming the masters of their domain, and that is simply cosmic.